All right, so get this. We're going deep into super heavy elements today.
Mm.
You sent in a Wikipedia article, so I'm guessing you already know the basics.
Yeah.
But want to go way further. Not just uranium is big and that's it.
Right, yeah, we're talking about going, like, off the charts of the periodic table, elements so heavy you won't just find them lying around.
We got to make them.
We have to actually make them.
Okay, so that's already, I'm hooked.
Yeah.
But hold on, before we even get to the, what even is a super heavy element? What makes these guys so special?
So basically, anything with an atomic number over 103, that's a super heavy element. So more than 103 protons jammed into that nucleus. These are like the champions, like the heavyweights of the periodic table.
Sure.
Way down there past the actinides, that's, that row below the main table.
Right.
Sometimes they're called transactinides or transuranium elements because, well, they come after uranium.
Gotcha. And to make things even cooler, we've never actually, seen a chunk of any of these elements. We're talking making and studying, like, individual atoms here.
Yeah, it's like atomic level craftsmanship.
It really is.
Like, how do they even do that? Well, they take lighter atoms and smash them into heavier ones, like crazy speeds. We're talking almost 1/3 kilometers per second.
Hold on, is this like some kind of atomic billiards we're talking about here?
Kind of, but it's not just like, whacking them together and hoping for the best.
Right.
Because the nuclei, they're positively charged.
Okay.
And like, well, magnets, the same poles repel each other.
Right.
They don't want to get close. So it takes huge energy to overcome that and get them to fuse.
So it's like trying to force, like, the north pole of two magnets together.
Exactly.
It's going to take a lot of force.
Yeah. But even then, there's no guarantee they'll fuse. The chance of them sticking, it's called the cross-section.
Okay.
And for these super heavy elements, it is tiny.
Oh, so we could put in all that effort and still not get a new element.
Yep.
That's a high-stakes game.
And that's just the first part. Even if they do fuse, you get this thing called a compound nucleus. It's super unstable.
Oh, so like...
Think like a house of cards ready to just fall apart.
So it's a race against time?
Oh, yeah, totally. It either splits apart, what we call fission, or it shoots out energy, neutrons, gamma rays to, try and stabilize. And this is all in like a fraction of a second.
Okay, I'm starting to get just how challenging this is, but hold on. If these elements are so short-lived, how do we even know we've made one? We can't just like pull out a magnifying glass and take a look.
Right. That's where some serious detective work comes in. They use these things called surface barrier detectors.
Okay.
Think of it like super sensitive cameras that can capture the impact, where the new nucleus hits, how much energy, and the time of arrival.
But how does that tell us we've got a new element?
It's the decay chain.
Yeah.
So when a super heavy element decays, it doesn't just vanish. It turns into like a series of lighter elements, and each one has its own like fingerprint. And the scientists piece those together like a puzzle.
Oh, wow.
From the detector data to confirm, yep, we made something new. It's pretty amazing.
So it's like a cosmic game of Clue.
Yeah.
But instead of Colonel Mustard with the candlestick, it's element 118 decaying into element 116 with an alpha particle.
I like that analogy. And it only gets tougher the further down the periodic table we go. Those half-lives, how long it takes for half the atoms to decay, I think it's super short. We're talking minutes, seconds, even milliseconds sometimes. Like, take seaborgium, element 106, longest-lived isotope, only 14 minutes.
14 minutes. I could barely grab a coffee in that time, let alone, like, study an element.
Exactly. It's a whole different world studying their chemistry. You can't just, mix it in a beaker like other elements.
Right. Yeah.
We're working with, like, tiny amounts that exist for, like, a blink of an eye.
Okay. This is way more intense than my high school chemistry class, I'm telling you. I'm dying to know more about these, like, crazy properties.
Yeah.
Can we get into that?
What's really wild about these super heavy elements is they're not just, like, filling in the gaps on the periodic table.
So it's not just about, like, bragging rights for making a new element.
No, not at all. We're talking about the edge of what's even possible. Like, the very limit of how much you can cram into an atom before it just falls apart. By studying them, we learn not just about new elements, but like the fundamental forces that hold everything together.
Okay, you've officially blown my mind here.
Yeah.
So it's like these super heavy elements are a window into like the core of reality or something.
Kinda. They're testing our theories about physics, making us rethink how atoms even work. And one of the craziest things to come out of this research is this idea of islands of stability.
Islands of stability. Okay, you're going to have to break that one down for me. It sounds kind of mystical.
Well, it kind of is. Think of it like searching for a hidden paradise. See, as you go up the periodic table, elements get more unstable, right?
Right. Shorter half-lives, they decay faster.
Yeah, exactly. But the math, the calculations, they suggest there might be these special combos of protons and neutrons.
Okay.
Where instead of getting more unstable, you hit these little pockets of, well, stability.
Yeah.
Like islands in a sea of like atomic chaos.
So instead of that trend of just getting more and more unstable, we could find these like stable spots.
Yeah. And these islands, they're predicted to be way up there in the super heavy element range. And if we can make them those elements, they could hang around for much longer, maybe even years.
Now that would be a game changer.
Oh, yeah.
Being able to like actually study these elements, not just for a few milliseconds. What can we learn from that?
It'd be revolutionary. We could learn so much about how the nucleus is structured. Maybe even find whole new ways to use them. Who knows? We might unlock some crazy new power source or something.
Okay, now I'm imagining scientists on this like treasure hunt across the periodic table looking for these islands of stability. What are some of the biggest roadblocks they're facing on this quest?
Well, like we said, just making these elements is hard enough.
Right. Super low cross-section.
Exactly. It can take, like, months, even years of bombarding a target.
Wow.
Just to make a few atoms of a new element.
Talk about patience. But even if you make it,
it
sounds like studying it is a whole other beast, right? Especially with those super short half-lives.
Oh, totally. Try running an experiment on something that only exists for a few seconds. And you can't even see it. It's so small.
It's like
trying to perform surgery on a hummingbird's heart while it's still flying.
Okay, that is a wild analogy.
Yeah.
I'm guessing it takes some pretty innovative techniques to study these guys then.
It does. Scientists have had to get really creative. They've come up with amazing stuff like single atom chemistry, where they can study just one atom.
Oh, wow. At a time. Talk about pushing the limits.
So with all these challenges, what have we actually learned about how these super heavy elements behave? Do they follow the rules, or are they total rule breakers?
That's where it gets really fun. Remember those relativistic effects we talked about?
Okay, yeah, refresh my memory. Relativistic effects.
So basically, when things are moving crazy fast, close to the speed of light, weird stuff starts to happen. It's like Einstein's theory of relativity, but on an atomic level.
So because these elements are so massive and their electrons are zipping around so fast, they don't play by the same rules as the lighter elements.
You got it. And it can totally change how they react, how they behave chemically.
Yeah.
Some do follow the trends we expect, but some throw us a curveball.
Like oganesson, the rebellious noble gas.
Right. Oganesson, element 118, it's predicted to be way more reactive than other noble gases because of these relativistic effects. It's like the black sheep of the noble gas family.
Yeah.
And that's a big deal, right? Because noble gases are supposed to be like the loners.
Yeah.
The ones who don't react with anything.
Exactly. So oganesson being reactive, that challenges our whole understanding of how these elements should behave. It's like finding out that introverts actually love going to parties.
Okay, I love that analogy. Yeah. So we're not just adding elements to a chart. We're shaking up our whole understanding of chemistry.
You got it. Super heavy elements are a constant source of new discoveries, forcing us to rethink the very building blocks of the universe.
It's amazing. Like, we can create these elements one atom at a time, and they're telling us about the universe. I gotta hand it to these scientists.
Yeah.
They're not just dealing with physics. This is some seriously mind-bending chemistry, too.
Oh, yeah. It really shows you what we can do, human ingenuity. And the best part is, it might not just be, like, theoretical stuff. This could actually have real-world uses someday.
Wait, hold on. Practical applications. You're saying super heavy elements can be more than just, like, science curiosities?
Totally. Think about it. Some of these elements, they might have unique properties, in their nucleus. We could use that for, like, medical imaging, maybe even cancer treatment.
Wow. So we're talking about, like, improving healthcare with these exotic elements. That's incredible.
It is. And honestly, who knows what else we might find? Especially if we find those islands of stability.
Right.
And figure out how to make these super heavy elements last longer.
Okay, now I'm really seeing the big picture. We're not just adding boxes to the periodic table. We're opening up possibilities for, like, new technology, new solutions to problems. It's like science fiction coming to life.
I like that. And as we're wrapping up here, I want to leave you with something to think about. Imagine a future where these super heavy elements, the ones we thought were just like ideas, they're part of our everyday
The
lives.
future with super heavy elements in our devices, helping us fight diseases,
Yeah.
solving all sorts of problems. I want to be a part of that future.
It's pretty exciting, right? And as we've seen today, going after knowledge, it leads to the most unexpected discoveries.
It makes you think, we're just barely scratching the surface of what's out there. Who knows what else is waiting to be found in the world of super heavy elements? It's a pretty amazing thought.
The journey's just getting started, and the possibilities, well, they're pretty much endless.
And on that note, we've come to the end of our deep dives into the world of super heavy elements. Hope you enjoyed this journey beyond the periodic table, and thanks for listening.